Hello.
Hey, Luca.
Hey. So, what's going on? What a week. Well, not this one, the previous one.
Yes,
Yeah, we
GTC.
were. Yeah, we were in San Jose with GTC. We even got to see the keynote, right?
Yeah, that was great.
Yeah, we
But
had VIP treatment, right? We got in, no line, got in the lounge, and then got really good seats. That's what you get from writing a compiler.
right, and so actually, you showed me like the one of the T-shirts that Jensen shot into the crowd. Now my daughter has a cool T-shirt.
Ah, nice.
Didn't stay with me very long.
Yeah, yeah, because at some point Jensen came out before the talk. Everybody was getting ready, blah blah blah. He came out with some kind of t-shirt bazooka, uh, in colored in green, like Nvidia green. So everything was on
Right.
brand. He came out with his leather jacket and shot a few t-shirts. We didn't get it, but on the way out, there was some person who left it on the floor, and so we got it.
Yeah.
So opportunistically, so. All right,
So
and then yeah, and we have some like this episode will be a bit of recap of what happened at GTC and some new stuff that we presented there, and kind of the how do you say the fall? How do you say that? The fallback? No, the outcome, whatever, the consequence of GTC.
the
So
upload.
the yeah, we'll see something about that. But then we had a talk on Thursday, which was great. It will be posted. Do you know when it will be posted? In a few days,
So
I
I
believe.
think it was 2 weeks or so, so it will be another week.
Mhm.
So the people who have registered for the conference, they can already watch the talks, but
Yeah,
I guess they want to market it like with a bit of delay. I didn't
yeah,
try
yeah,
logging in yet.
yeah. So basically, we'll post in a future episode. We'll post the link to the talk. But basically, the room was pretty packed. Like it was like full house. Was how many? Like 150 people or
Yeah,
maybe more,
something like that.
something like that. It was a decent sized room, so it was very full. Then we got a ton of questions afterwards, and I think all the questions were quite on point. And I think they were all kind of pointing to the fact that, yeah, I mean, the fact that hardware is getting harder to use,
Yeah,
and uh,
the not only like a given chip will be like more elaborate, right? And back in the day, you had like CUDA cores. Now you have all these tensor cores and for various precisions, and they have various like properties, and they also widely vary.
yeah,
Um, but then you not only have this one chip gets more complicated, but of course the connection between them that is just crazy, right?
yeah,
So
yeah. And even in the way they are, not only single chips are connected with each other on the same board across machines with different ways of communicating, reducing. If you and overall, I think one comment that I captured was that new hardware is getting a lot less tolerant to being used suboptimally compared to before. So if you before you had Ampere, you could run something optimized, not optimized. Yeah, it would be faster and it great. Then, but if you move to Hopper, chances were that you got the proportional speed up to how much money more you spent, apart from memory being larger. With Blackwell, that's not necessarily the case, from what I understood. Like you need to use it well to get a lot of speed up, and if you don't use it well, then you get speed up, but not as much as proportional to how much you paid for the
right,
chip.
yeah, I mean, obviously the Jensen presentation that had like a lot of graphs and stats and a Pareto frontier and for inference, and so that means like there needs to be a lot of thought to be put into how you set things up in much detail, because you had
Yeah.
a whole rainbow of configurations for inference that have all different performance characteristics, and so there's a trade-off to be made between the individual speed of one stream and the total throughput.
Yeah, exactly. And you can argue that, yeah, their code bases, they're fixed. Transformer is always the transformer. But go look at the Quen Omni paper. Like that thing, that Quen Omni is a model that came out like what, 2, 3 days ago, that
Right.
does audio, video, image, and text input, and then speech and text output. Architecturally, that thing is not like super simple. Yeah, it's a transformer architecture, but if you need to make that thing fast, then you have so many details, and so it like uh, the building block is still attention, but there's a lot around that building block, and so I think in the end, how do you deliver optimizations to that kind of model is very tricky. And as hardware gets trickier, it gets incrementally more tricky. And so that's I think why people are realizing that, at least people in the room were realizing that having a optimization delivery mechanism that is Thunder in the end, that Thunder wants to be, and it's not the only one, but I think it's the one that we think has great shots at kind of being all encompassing, from distributed to precision and so on. It's so important. So
Yeah, and
yeah, go ahead.
and obviously, like, people want to still have good control. So obviously, I think part of the success in the talk was also that we promised, like, not only make my model fast, but show me how you did it, right? And
Yeah, and
so
that was the title of the talk, and this is what I'm gonna show in a second. Let me see. Yeah, let me share. Maybe we'll just share a bit of the slides that we had in the talk as
yeah,
a preview to our trusted following.
so
And
so obviously, like, the talk was exactly like the Thunder sessions, but it was, well, almost rehearsed, right?
yeah, also because it wasn't live coding, so by definition, everything worked out.
Right.
Uh, so anyway, oh, that's not the one I wanted to show. Interesting. Let me stop sharing. See, you can still you can
Yeah,
still
the
make
draft.
mistakes. Yeah. This was the draft. Sorry about that. Yeah, let me just get the actual talk. See, you know, this is the place where we can make mistakes, even if we have a presentation.
Well, we have skills. Ours is to make
Yeah,
mistakes.
yeah. Let me just. All right, it's downloading. All right, I get it. Great. All right, so let's pretend nothing happened, and let me share my screen again. And that is the one. Yeah. All right.
Yay!
Yeah. So we were saying compute is evolving, and this is
And you
the
and you
big one.
can see how the sausage is made. You start with a wall of text, and then you just put in those fancy machines, right?
Yeah, this is a fancy machine that is, I think it's about $3 million each. It's a 72 GPU system, and you can imagine, like, and it. You know what's the weight of this thing?
No, like a ton.
At 1.4 tons. And it's
God.
all copper. And it's all copper, basically. The weight is
Yeah.
from the copper, and the copper you see it here. It's all the wiring because they didn't even use optic fiber because they said, yeah, of course, optics are much better than copper, sure. But then you need to convert electrons to photons back to electrons, and that is not fast enough. So
Well, and it
here,
takes too much power, right?
and
That is
it takes
what
a
it
lot
said
of power.
too.
Yeah.
Like Jensen went on the stage with the cables,
Yep.
and he said, "No, none of this in in the NVLink thing."
Yep. Yeah, yeah. And then they also presented a switch, optic to electron switch that
Yeah, like
they created.
on-chip conversion, right?
Yeah, exactly. Because otherwise it would be too expensive for data centers. But within the same rack, there's no optic. And and so it's 1.4 tons of copper, of which probably 1 ton point something of copper, and all the rest in other type of material.
So,
But
do you think this is actually a photograph because it has these tiny feet it stands on?
I don't know. It
I
might
don't know.
be an omniverse simulation of that.
Do I believe that this is like, I don't know, 350 kilos per this tiny phone?
Yeah, like that would be like what would be the pressure in here? Probably like larger than the pressure on a black hole. I don't know. Yeah, probably.
Well, anyhow, these things exist
Yeah.
even
Yeah.
if they have like different feet.
Exactly. So, and then, going from a model that has, that runs across GPUs among machines of like 8 of them with different interconnects to something like this, like trade-offs change dramatically. Plus, this thing is made with GB200. And GB200 have 2 GPUs and one ARM CPU with a unified memory on it. It's called here extended GPU memory, where you can do offloading really efficiently there. And so again, would you recompute on backward? Would you offload for backward now? All the trade-offs change. And so, but does it make sense to offload when you don't have a GB200? Yeah, probably not, right? At least you need to have a Grace Hopper or Grace, again, Blackwell
Right.
architecture. So the computation needs to transform itself in order to adapt to one of these. And then modern day challenges is how do you get access to compute and how you use compute as its full potential, which is incidentally both things that we help our customers with at Lightning.
Yeah.
And then our friends at NVIDIA, before the talk, they ran a final set of benchmarks where we took LGPT and then ran it through PyTorch, eager. And here it says optimize because I wanted to create some suspense. Like this is the theoretical speedups you can get from the old architecture, blue and red, and the new architectures and yellow and green. And you can see that the gap. Well, first thing you can see that Blackwell B200s are faster, can be much faster than the previous generation, but also that the gap between, this is a fold increase, right, for different sizes,
Yeah.
that the gap between non-optimized and optimized is larger for the new generation.
Yeah.
And as you optimize, as you use optimized implementations of various things and fusions and so on, these differences are gonna be more and more important. Like here, you can go from a threefold speed up compared to 100 H100 PyTorch eager, so non-optimized.
Yeah, I mean,
To
basically you
4 times.
get a 20-ish% speed up on Hopper from optimizing, but on Blackwell it's more like 50-ish%,
Yep,
right? And that's
exactly.
no small thing.
Yeah, and it comes from many things. It's just not one thing, right? So you need to put together many optimizations. And how do you know as a model implementation person what to do where? Because it's a composition of multiple things. And so here's where computing transforming code, transforming computations, and composition are all so important. And this is what we've changed in Thunder in the last few months, and it's kind of a happy place to be, where it's kind of a validation of what we think is important. And well, we talked about this a lot of times, but like this, ideally, because you don't know the combination of optimizations that will be right for your setup. Like, are you running on a rack? Are you running on a set of machines that are loosely interconnected? And all this will have different trade-offs. And so, yeah, ideally, you would like to take your model that was written for single machine execution, and then just scale it out and add more optimization to it. The reality is a bit different, though, and it's a mix of automated and manual. Like, I want to use a hand optimized kernel in combination with other things that are automated. But the reality right now, and we know, is that all the optimized code bases that are out there are very, very specific. And unfortunately, one code base will have to encompass all the variation of running on different topologies, different hardware, and so on. We're kind of reiterating the same concept here. And so this is why we created Thunder, like we all know it. So we'll gloss over this. And something we presented this time around is the new API. We introduced it a few episodes ago, the recipes, which are still there. So the new entry point for Thunder, and it's not like that we're not deprecating ThunderJIT, which is the lower level API. Now we have a higher level API that sits on top of both ThunderJIT and ThunderFX, which is the path that goes through Dynamo, is Thunder Compile. So no matter what route you're following underneath and what kind of lower level options you're passing to ThunderJIT, Thunder Compile is kind of a non-expert entry point, which I think is not just non-expert. It just captures everything that you need to pass to the lower level API in a very nice way. And so Thunder Compile, go ahead.
Yes, so basically, I mean, it's a translator, right? From the high level to the lower level call.
Yeah, and we'll see it in a second in what was your section. So this is where I was doing the talking, and then passing on to you for serious stuff as usual. Well, a novelty for people who are following us.
You did the things that the people liked, and then
I don't know about that. So yeah, but wouldn't it be nice to say, okay, we have a set of plugins, and here what are plugins? Plugins are, for the people that followed us. Thunder has look-asides for telling the ThunderJIT that instead of executing one function in Python, it should take another route. And this is how we build a trace. So look-asides and transforms and executors. And all these three things do different things in different places, but basically from the user's perspective, they're just, I want something to happen. Whether it happens in a transform, in an executor, or in a look-aside, the user is not really concerned with that. They just want FSTP to work or FPA to work, and so on. And this is why we created plugins. Plugins can be passed as one single string, a list of strings, a list of objects. And you can also say FSTP object and then pass configurations to it. That's a novelty for our podcast, music.
Yeah, stupid me. I spent so much time finding a place with good wireless that I forgot to switch off the mobile.
No worries. All right, so we all know this. We don't have to go through this, of course. Here we were trying to kind of introduce how Thunder works, but it's a good refresher for the people who just joined maybe. And these are some of the transform. We had PP and TP grayed out because PP we haven't upstreamed it yet. We are using it within Lightning, but it's not back. It's not in repo yet. And tensor parallel we have something, but we need to evolve it. But it's very clear. It was very clear to people that one of the key advantages of Thunder is distributed. The ability to think about distributed the same way you think about other things like, um, you know, AutoCast, Chronograph, whatever, like all the other optimizations.
Right.
So and how they interact and so on. And so we'll be working more around this in the foreseeable future. This is a selection of executors that we have, and this is what was your part essentially, where we wanted to go through a fine tuning example of how would you fine tune DeepSeek R1 70 billion distill.
Right. And you just do Thunder compile, of course, and that, like, if we want to show how we did it, we will see in a bit what it translates to. So plugins and recipes are the one thing, and then the ingredients will be transforms and executors.
Yeah, and so these are all the optimizations that we had in our code essentially. So cuDNN SDPA, low precision. MXFP8 is a format that only exists on Blackwell, and it's basically an FP8. I don't know if we already talked about it. It's FP8, but when you quantize or lower the precision to FP8, you have some scaling factors, and the scaling factors can be tensor specific or raw specific. And MX FP8 are tile specific, and they are more effective that way. So training using MX FP8 is actually better.
Yes. So basically, it attaches the scaling factor right to the FP8 data, right? Instead of having it as a separate tensor, as for example the R1 typically shows it, right?
Yeah, and then FSTP, and then the other problem we talked the other time, where you want to load and save a checkpoint, but then you have the problem of how do you load it in something that has been transformed.
Yeah. So here's the thing, right? We replace the FSTP with an FSTP transform and the FP8 with the transformer engine executor, and that's all there is to it, right? And of course, the recipes they can do more complex things too, but basically it's an easy way for modeler or for optimization curators to give you a full set of optimizations.
Yeah, exactly. There's one open point, which is ordering, that we'll have to tackle in the next few weeks or months. So how do you make the list of plugins not order dependent so that people don't shoot themselves in the foot? Whereas transformers and executor can be order dependent and are order dependent, but we would like to make this not order dependent. But that's a problem for later. And then we talked a bit about, I think we showed this the last time.
This should be known to people following the podcast. So the various intervention points of the transforms, which are, of course, at the setting up of the module, the materialization on a given device, but also loading and saving the state dict, which is kind of one of the things. It's a small thing compared to all the other things Thunder does, but it's a really, really neat mechanism to change those optimizations and still be able to work with checkpoints from the full thing and create checkpoints for the full thing.
Yeah, usually people don't care about checkpointing, but it's actually one of the biggest source of frustration if you do actual work, precisely because you don't think about it. When it shows up as a problem, then it's a massive yuck shave. Like, I'm not here to solve this problem. I'm here to solve the problem that I'll have when I load this thing in memory. But I'm unable to do that. So I'm completely blocked. I'm spending time there. I should spend time on the other side. And so, I went through it so many times that a good story for loading and saving is a lot of the convenience.
It really is part of the composability that we have here on the next slide, that you really need to have states where you can say, okay, this is a thing that I can work with, and then the transforms, they modify whatever the state is, and this can be on the module, in the traces, loading the state dict, or like a reverse direction for saving the state.
Yeah, here we are showing FSTP. So in FSTP, we went through it in the last couple, 2 or 3 episodes. You have a sharded state. So each GPU owns just a shard, so a portion along one direction of a weight. And so when you load it from a full checkpoint, you need to only retain, or either load or retain just a fraction of it. And then when you save it, you need to assemble the full from the shards. So you need to go through this process.
Yeah.
And if you do it at the wrong time, you will go out of memory. And so that's where,
and so
in the wrong order, right?
For full disclosure, the arrow on the bottom right, that needs to be flipped, right? It should go the other way.
Oh, yeah, this one. Yeah, for sure.
Yeah,
for sure.
But
yeah, well, good.
So it goes.
All right. So, and then we showed a bit of distributed, like what happens when you transform a trace and you add distributed. And interestingly, you can do this on the forward, and then by having an explicit representation of the trace in the backward, you can do it from the backward in a very inspectable way.
Right. And the like avid listeners will know that we cheated here a bit, or I did. And so the first 2 lines are, of course, from the prologue, and the last one is from the compute trace. And similarly, at the bottom.
Conceptually, that's what happens. Yeah.
Interestingly, currently we swap against the synchronize, and this is actually done through a custom derivative formula that we replace it with the actual lower level that does a bit of lowering to the actual thing, and that's because we want to have good access for doing it on the forward and the backward. But yeah, so here is like how the transform works, and of course it's relatively simple. If you have a sharded parameter, then you just replace the parameter, or you insert like a synchronization point, and then you swap the original parameter where it's used with the newly assembled one from FSTP. And so the nice thing is that this is like relatively easy to write. It's 400 lines of code. But it's also kind of transparent then to the user that they can look at the before FSTP and after FSTP trace, and they see the difference, right?
Yeah, and one of the things is in FSTP, and we briefly touched upon it previously, is that go back and think about the big cluster. And connection speeds there are massive, like they're super fast. And so what you synchronize when, and the amount of memory is also large. But of course, the larger machine you have, the bigger model probably you'll end up training. And so the strategy by which you say, okay, let me synchronize this bucket of tensors before I do to assemble the full parameters for a few of them, so that I can run my forward, and while I run it, or backward, and while I run it, I already communicate, because I want to overlap computation and communication. I already gather more parameters and so on. And so how early to do it, and how to break up the buckets of parameters that you synchronize, ultimately is going to be dependent on the amount of memory you have and how fast interconnects are. So, and how your model is built, because, it may be large in a section and smaller in another section. So if you do every n, that might not be representative of like you getting the maximum out of your system. And having a 400 lines of code FSTP transform allows you to go in there and reason about it. So
Right.
the logic is not scattered around a very complex code base. It's actually all there. And then you can hack it and you can optimize it. I think this is ultimately interesting to me. And then lazy loading. We already talked about it. And then the inspectability part was also something that interests people, right?
Yeah. So look, we spent quite a time staring down the traces, and if you remember the episodes before Christmas, we did a lot of things with this examine memory for traces, where we looked at what's using memory, and then we found that some things got reordered, and that wasn't good for the memory in the checkpointing. And so this is like really nice that we have this inspectability. But then there's also, we can not only debug not only inspect the traces, but we can also inspect the actual run. And so there's a debug transform. We use this to compare the calculated memory with the actually used memory. And so we looked at this quite a bit also before Christmas. And then there's the NVTX profile transform, which allows you to get like nice markers for each line in the trace on your NVTX profiling, which is the fancy NVIDIA profiling, right?
Yep. All right. So I think we talked about custom transforms that we know about, and then there was some acknowledgments, of course, of the great team at NVIDIA. So this was our talk. And before our talk, a couple of talks before ours, there was this talk with Alban from PyTorch, and Aiden and Sayed from NVIDIA. Who were talking about very interesting things. So I want to briefly touch upon it because it connects to what we said a minute ago. So first thing is, how do you record memory profiles? And there have been some improvements in the memory profiling tooling for PyTorch, and I think it's really cool. And I think we should take a look at how to integrate better here, where you can get a view on how your memory is shaped during passes. And here it's the actual memory. You cannot simulate it. With Thunder, you can simulate it, but here you need to make it happen.
Do you want to show it? Like show the memory profile they showed?
Am I not? Oh, sorry.
It's still on the talk, I think.
Okay. I had 2 tabs in my window, and I was hoping that...
I saw the other tab, but... Well, we saw the header for the other tab, but we didn't see the tab.
Here, this is the talk. This is the talk, sorry. I thought I was showing it. Thanks for reminding. And this is a really nice talk by, again, Alban, Aiden, and Syed, who showed the new profiling tools in landing in PyTorch, and we'll be really happy to make good use of those moving forward. So they showed an example where there was big difference in memory during training. So there was the first iteration here, and then the second iteration. And so this was a peak memory for the first iteration. This was a peak memory of the first. And so there was an explanation on why that happened. But overall, I think having this kind of tool, this, of course, as I was saying, after the fact, like you need to make it happen. So if you you won't see past the of course, but then you can make your model smaller, or load a few blocks and not the whole model, and see the dynamics there. It has to do with how when gradients are cleared and so on.
Right.
Which again is something that you need to know. It falls in the realm of things that you might not know, and that
Right.
It's not how people use PyTorch usually. That's also something. Um, and yeah, and I suggest when this presentation comes out, you take a look. It's very detailed on having multiple CUDA streams and how they signal each other that there's something that can be deallocated essentially.
Yeah,
But the other thing,
the trouble was here that like while in the code it was clear that the memory could be freed after something,
yep.
there was a different stream that released the memory and that acquired the memory, and then they weren't synchronized, and so they overlapped, and so you got those memory spikes,
Yeah,
right?
overlap, but not always.
Yeah.
Depending on, because when you have two independent streams, things are not deterministic anymore, and so sometimes normally they wouldn't overlap, and so things would be okay, until the 100th iteration or the 10,000th iteration, where some overlap happened for some reason, some struggling computation or
Yeah.
communication, and the system woomed. And I say, what? Like, it was fine until now. Like, why did it go out of memory? And this is that's why.
I imagine during the llama training, the
Exactly.
meta guy in charge of making sure it runs through the weekend, he really
Yeah.
hated that.
Yeah. Meanwhile, R1 was coming out. Must have been a kind of shit show. But it's that's a reality of things. So there was a really super nice presentation here. And then the other is that there's an allocator that in PyTorch, as we know, and now the allocator runs on a kind of pool of memory. But now the memory pool is configurable. So you can use different memory pools in the same program. And the different memory pools can use different allocation mechanisms. And that can be controlled by different subsystems. So, for example, there's an API that allows NVLink sharp reductions to happen, which is basically, instead of going through this route when you do a reduction across GPUs, instead of communicating through the PCI Express and InfiniBand, it goes directly through NVLink. You would think that this happens anyway, always, or when needed. Nope, you need to make sure you put those tensors that you want to reduce across this link in a different memory pool. And this tells you how much detail there is and how many people would even realize that they need something like this.
Yeah.
You need to be expert level there. And this is, I think, where we can also help. By transforming computations on behalf of users.
You need to have more than 256 GPUs for that.
Yeah, okay. fair. And chances are in that case that you have people that know what they're doing. But anyway.
Well, you never know, right?
You never know. And then, extended GPU memory, which is something that I mentioned, which is when you have a Grace architecture, you have an extended memory that extends beyond HBM. And then you want to offload. But if you offload to CPU, then you offload to CPU. If you upload to extended GPU memory, it will be way faster. So when you do offloading, you want to use this memory pool for the offloading. And again, you need to use a different memory pool. So very, very interesting. And I don't want to harp too much on these things, but things are getting like super interesting, but at least and as well as very complicated, and they have a massive implication on how you use your compute. Just to conclude, I would like to share my screen again, and then we can go. Unfortunately, today you won't see the real interesting thing, which is Thomas coding and teaching cool stuff. It will be me sharing my screen. But, what can you do?
We'll return to the regular program soon.
Exactly. So okay, can you see? Yes. Okay.
Yes.
So right before the talk, exactly. Right before the talk, we updated our README, which is great.
Which is what we usually do, right?
Exactly. Yeah. So let us know about the README, but essentially, yep.
So here, if you want a new version of Thunder like to be released, you just need to invite Luca and me to some nice
To give a talk.
conference at a nice location. And don't forget the VIP.
Exactly. This finally will trigger all the releases. In fact, we released the Thunder 022 and
Yeah, last week it says.
exactly. And so, and then, yeah, we have the new API here, and we have a few examples. Here we
Yeah.
have an example with a backward from LeadGPT. We also have other examples. And among the examples now, we have transformers. And we tried transformers, and we had to use a manual recipe for transformers up until last week, I believe, because there were some quirks in the transformer code that introduced data-dependent control flow. But we just saw, thanks to a coworker, that Transformers 450, which is the latest release, solved these problems for us. And so basically, you can just compile Transformers using Thunder, and it will just go very smoothly. And hopefully, we'll get you a speed up, and maybe I can show you how it is. Here, probably plugins will have to be more fleshed out in the next few weeks, but that's okay. All right, so I have my L4 L4 Studio here, and I want to show you the new directory examples quick start. And we have a few examples here. One is Hugging Face BERT and the Hugging Face LLM example with Llama and other examples here. So I'm going to run the quick starts directly. We don't have a lot of time, but we don't need a lot of time.
Yeah, that's why it's a quick start, right?
Yeah, exactly. So here I'm using a benchmark n, which basically means run this thing and take the time n times. And then you can swap in the model name. Here we identify what device we're on. We initialize the tokenizer. We say, okay, on this device.
Should we start it
the model.
and then
oh yeah
look at it more?
Yeah, absolutely. I can fit. See, you know the tricks of the trade of
the multitasking.
Yeah, exactly. Here we just okay, we load it in bfloat 16 precision. We set it for inference essentially, and then we create an input using tokenizer on the same device. And we have a generate function. And why we have a generate function here without, and we don't just call generate, it's just because we need to call it a couple of times and pass it to benchmark. But otherwise, you could just run model generate manually. And here we taking the time for running the model through PyTorch Eager. So Hugging Face Transformer, PyTorch, and then let's take this, get this out of the way. Okay, great. And then we call Thunder compile, and we again run it and take the time. And here we see that it just compiled, and I mean that's a pretty nice speed up you get on an L4 from 2200 milliseconds, so 2.2 seconds for the generation of the same number of tokens, of course, 100 tokens. In Thunder, you get 1200 milliseconds, so 1.2 seconds. So that's a pretty massive speed up. And this is just with the default executors. So NVFuser is fusing its thing, and you have SDPA for the attention running in the back. But overall, yeah, it's a pretty nice speed up. And then if we get to BERT, for example, here we're also showing something else, like it's exactly the same example. But BERT is a model that will create will embed your code, your input. And so right. This is the input, and we'll create an embedding for it, very roughly speaking. And here we are compiling it, and we Since it's a small model, the point with a small model is that it will be massively latency bound, in the sense that the kernels will take so little time to execute that you'll spend more time launching them than executing the kernels. And so what you can do in that case is just reducing the overhead. And what this is a terminology that Torch Compile introduced. And essentially it means we want to capture the computation with CUDA graphs and then just schedule all the kernels one after the other without CPU latency. And it makes a massive difference. So Eager takes 8 milliseconds to run this. This is BERT base. We can also run a larger one. And okay, we are acquiring it now, and we'll be running it in a second. And we'll see that Thunder saves you some time.
Yeah. So BERT was the original thing, right? It was Was it the first transformer? Like the attention is all you need transformer,
No, attention is all you need was a encoder decoder architecture.
Okay, right.
Like more like T4, but T4 had T5, but T5 had kind of more losses and so on.
Right.
But it's the full encoder, which is BERT, decoder, which is GPT essentially, together. And
Right.
BERT is basically the beginning of the transformers is all you need until until it gets into the decoder. Okay, so we see that Thunder saves you a millisecond, but then Thunder with CUDA graphs will save you a lot more time, because all this time is basically spent launching kernels and in CPU latency. So the GPU is so fast, the CPU cannot keep up. And this is just pure CPU overhead. Yeah, I think BERT is the first model that landed on Hugging Face transformers, where Hugging Face transformers was not called Hugging Face transformers. It was Hugging Face something else. I think BERT was the first model to land there. And it basically the first model that got, where having a pre-training and fine-tuning thing kind of showed that you can really make it work that way. So it kind of changed everything. And interestingly, I know you're not a fan of those, but one of the latest text diffusion.
Hey, you always say that.
I know. I did it on purpose.
I was just saying that the diffusion models, the text diffusion also, oh wow, it's 1 and 1.4.
Yeah, it's all latent, it's all overhead. But see, you change one flag, we do the thing, you don't have to worry about it, and now it's like what? X hundreds times faster. So that's the way we like it.
Yeah.
But BERT is the base model for the latest diffusion language models. It's pretty interesting. Yeah. It's the BERT architecture with the diffusion models for text. Anyway, this was a lot of fun, at least if we say so.
Yeah.
And next week we'll be at a nice offsite with the whole Lightning team. So we'll be thundering a lot, and have fun.
We will. So see you there.
Luca. See you in a few days. All right. Bye, everyone. See you next time.
See ya.